Next, we want to talk about the Earth's moon. It's our nearest neighbor in space. Once the frontier of direct human exploration, it was born in a cataclysmic event into the original molten state. The moon is now a dead world. No plate tectonic or volcanic activity, and no air. It has suffered a lot of impact barrage early on, and it plays a major role in eclipses and tides. The moon is 1/4 the Earth's diameter. Its gravity is 1/6 as strong. So if you weighed 180 pounds on the Earth, you would weigh 30 pounds on the moon. The astronauts called it a place of magnificent desolation, shapes of gray without color. The surface is divided into two major regions. The highlands, bright rugged areas composed mainly of anorthosite, a rock rich in calcium and aluminum silicates, and pitted with craters. The Moria, the large, smooth, dark areas surrounded by highlands, are composed mainly of basalt, which is more dense than the anorthosite. So the highlands, or paler areas of the moon, are rough and mountainous. And one of the Apollo spacecraft landed here. You can actually see a picture of one of the Apollo astronauts walking past the large rock in the highlands. One of the things that most dominates the surface of the moon are craters. They're circular features with a raised rim and range in size from less than a few centimeters to a few hundred kilometers. Some of the larger craters have mountain peaks at their centers. And recently we've discovered signs of frozen ice beneath the surface, and the ice is in craters near the poles of the moon, which are totally shielded from the sun. It's rare to see craters on Earth because they get eroded away quickly, but they do exist, as in the Barringer crater in Arizona. To give you an idea of how large this crater is, there's the 4-lane road coming into the crater. Another feature of the moon are rays. These are long, light streaks of pulverized material radiating away from many craters, and you can best see them in the full moon. These are a result of material being ejected from the craters. And actually looking at the rays, we can see when a ray goes over another crater, we know that this crater was created before another one. Another feature of the moon are rills. They're lunar cannons, carved either by ancient lava flows or by crustal cracking as the moon cooled down. These canyons can be quite long. This rill here goes back and forth over 100 kilometers or 62 miles from tip to tip. Now nearly all lunar features, craters, Moria, rays, are the result of impacts by solid bodies early in the moon's history. A circular crater forms when a high-velocity projectile disintegrates upon impact, and vaporized rock and fragments blast a hole in the surface. The craters that are formed are much larger than the meteorite itself. It's the explosion that makes the crater large. So we have some material coming down and striking, and these meteorites that hit can be going 20,000 miles an hour. They go so fast that they punch right through the surface. As they're going down, they're compressing the material underneath them greatly. Eventually it stops, and all that compressed material needs to expand, and it does so violently and explodes, sending material out or ejecta out in all different directions. And in the large craters, where it landed and where it was so compressed, when it comes back up, it leaves a little bit of a peak. In fact, you can see this yourself. Take some large smooth sand, drop a rock from a great height, and as it hits and creates a crater, you'll see the raised edge on the circle of the crater, and a little divot in the middle after you remove the rock. The highlands are the result of very intense bombardment by solar system bodies soon after the moon formed and created a solid surface. The mare forms when early in the moon's history a few large bodies over 100 kilometers in diameter struck the moon. Now, it's early on in the moon's history as it was first cooling down, and we had the solid crust but still had liquid in the center. As a large object comes and punches through the surface, the molten rock is able to come out and fill in all the lowlands of the moon. And we call that a mare, and all of them the Moria. Now the moon lacks the folded mountain ranges and variety of volcanic peaks seen on the Earth. And that lack of activity is due to the moon cooling off much faster than the Earth. The moon's higher surface-to-volume ratio relative to the Earth allows heat to escape from it faster. And being much less massive than the Earth, it also has a smaller source of material to supply heat. Now, one of the things the Apollo astronauts did is they brought back a lot of moon rocks so that we could do some radioactive dating on them. And the oldest rocks on the moon were 4.48 billion years old in the highlands. The Maria were all about 3.3 billion years. And if I look at most meteorites, and there are different places on the Earth that we can collect meteorites, almost all meteorites are about 4.6 billion years old. As we're going to see later, 4.6 billion years corresponds to the formation of the solar system. Now, what about the interior of the moon? It can be studied by seismic detectors set up on the moon by astronauts, and have essentially found that the moon is inactive and has a simpler structure than the Earth's. The surface layer is shattered rock chunks and powder from repeated impacts that form something called regolith that could be tens of meters thick. Regolith is basaltic in the Maria and anorthotic in the highlands. Regolith may extend to several hundred meters deep in some places. If we look at the crust of the moon, its average thickness is about 100 kilometers, although it's thinner on the side that faces the Earth. And the reason for that asymmetry is not clear, but is probably related to the difference in the gravitational force across the moon. Very few Maria exist on the side of the moon away from the Earth. Crust is composed of silicate rocks rich in aluminum and poor in iron. The mantle of the moon is relatively thick, extending down 100 kilometers down, probably rich in ovline, and appears too cold and rigid to be stirred by the moon's feeble heat. The moon's low average density tells us the interior contains little iron. Some molten material may be below the mantle, but the core is smaller and contains less nickel and iron than the Earth's. The relatively cold moon interior, its low nickel iron content and slow rotation imply no lunar magnetic field, and that was exactly the case found by the Apollo astronauts. The moon's surface is never hidden by lunar clouds or haze, nor does reflected spectra show any signs of gas, and hence there's no winds. The lack of an atmosphere means no erosion and extreme temperatures changes in the lunar surface. The lunar surface can get to 387 degrees Fahrenheit below zero at night and 253 degrees Fahrenheit above zero in the day. Now, there's no atmosphere for two reasons. There's no volcanic activity to supply gas, and the moon's gravitational force is not enough to retain any gases, even if there was a source. The lack of atmosphere and plate tectonics implies that the moon has been relatively unchanged for billions of years and will continue to be so in the foreseeable future. The moon's orbit around the Earth is elliptical, with an average distance of 380,000 kilometers and a period of 27.3 days relative to the stars. Determining the moon's distance can be done with high precision by bouncing a radar pulse or a laser beam off the moon. One of the things the astronauts left on the surface of the moon was something called a retroreflector. You can see retroreflectors, say, on the surface of a stop sign or in the plastic reflectors on your vehicle. If you look carefully, it looks like the inside of a cube with three surfaces at 90 degrees from each other. And light, when it strikes something like that, no matter what direction it comes in, will always bounce directly back. So if I shine a laser at the moon and hit one of the retroreflectors, it's going to come right back, and I can take the time it takes for a light pulse to go back and forth and determine from that the distance to the moon. The moon is in synchronous rotation. It keeps the same face toward the Earth as it orbits. It rotates once every time it orbits once, and that's called synchronous rotation. If we were to look at a particular lunar peak that maybe was pointing directly at the Earth, as the moon goes around, it's going to rotate, and so that same peak will be facing towards the Earth at any time. The moon's orbit is tilted about 5 degrees with respect to the ecliptic plane, It's also tilted with respect to the Earth's equator, which is very unlike most of the moons in the solar system. The moon is also very large relative to its central planet, again, unlike most of the moons in the solar system. So these oddities indicate that the moon formed differently from the other solar system moons. Before the Apollo missions, we had three hypotheses of the moon's origin. One, the moon originally was a small planet orbiting the sun and was subsequently captured by the Earth's gravity during a close approach, called the capture theory. Two, the Earth and moon were twins, forming side by side from a common cloud of gas and dust, called the twin formation theory. 3. The moon spun out of a very fast rotating Earth in the early days of the solar system, called the fission theory. Each of these hypotheses gave different predictions about the moon's composition. In the capture theory, the moon and Earth would be very different in composition, while the twin theory they would have to have the same composition. In the fission theory, the moon's composition should be close to the Earth's crust. Now, when the Apollo astronauts got there, moon rock samples proved surprising. For some elements, the composition was the same, but for others it was very different. None of the three hypotheses could explain these observations. So we formed a new hypothesis called the large impact hypothesis. The moon formed from debris blasted out of the Earth by an impact of a Mars-sized body that struck the Earth when the Earth was very young. The age of lunar rocks and the lack of impact site on the Earth suggest the collision occurred at least 4.5 billion years ago. The large impact idea explains many things. The impact would vaporize low melting point materials, such as water, and disperse them, explaining the lack of them on the moon. Only surface rock blasted out of the Earth, leaving the Earth's core intact and little iron on the moon. It easily explains composition difference with the Earth. And the splashed out rocks that would make the moon would more naturally lie in the ecliptic rather than the Earth's equatorial plane. And also the Earth's tilted rotation axis is explained. As the Earth formed and all the objects in the solar system formed, their rotation axis should be the same as the Sun. Since we're tilted, something large had to strike the Earth early on in our history. So as the moon's surface solidified, stray fragments from the original collision created the craters that blanketed the highlands. Few of the larger fragments created the large basins for the Maria to form. And by the time the Maria filled with molten material and solidified, little material was left for further lunar bombardment, so we have the smooth nature of the Maria. In 1961, President John F. Kennedy declared the U.S. would put a man on the moon before 1970. On December 24, 1968, 3 astronauts circled the moon for the first time. 7 months later, on July 20, 1969, Neil Armstrong and Buzz Aldrin were the first men to walk on the surface of another planet. They and other astronauts brought back pieces of the moon that allowed us to make the measurements above on the age and composition of the moon. It's really hard for us, who were not around then, to fully grasp what a huge accomplishment this was. It was our first big step in exploring the universe around us. And there's a great movie about one of the biggest failures and, quite frankly, successes of the Apollo missions called Apollo 13. If you have never watched it, I highly recommend that you do so. This is the end of our lecture on the Earth and the Moon. We'll continue with talking about the other terrestrial planets.